All right, maybe I will just start by introducing Qirong Ho. It's my pleasure to introduce Qirong. Qirong now is a co-founder and CTO at the Petuum, an AI startup recognized as one of the world's economic forum's tech pioneers. Petuum creates the standardized building blocks for the assembling AI affordable and sustainably. Dr. Ho holds a Ph.D. from Carnegie Mellon University and is part of the technical committee for the CASL open source consortium. Prior to his work at the Petuum, Dr. Ho provided a key artificial intelligence and machine learning infrastructure solution to the technology, banking, and telecommunication companies. Qirong today is going to talk about ML system for many. Okay, without further ado, Qirong, it's yours.
Okay, thank you very much, Lee, for the introduction. Hello, everyone at MBZUAI. This is my first time speaking at the university, so it's a real pleasure to see everyone over here. I'm going to share my screen right now and then start the presentation. So, a little bit of a forward to this presentation. I come in here with a background where I was once a person who created ML models, and then eventually came into this topic that I call ML systems, which is about the software and sometimes the hardware systems that are used to take these ML models or AI models into large-scale training and production. And one thing I've observed recently is that, and this is what motivates my talk, one thing I've noticed recently is that the capability gap between large and well-resourced organizations versus, say, universities or other small to medium organizations, or perhaps individual researchers. This capability gap has been growing for a number of reasons, for which we have to be thankful for, like the advances in capacity of different artificial intelligence models. But at the same time, these advances are just creating this widening gap between the big organizations and the small ones. And my talk will address some of the research themes around how we can make, the playing field a little bit more level, a little bit fairer for everyone. So kind of to motivate what I'm talking about here. So we are quite familiar, I think, with this idea of models that a team at Stanford is now calling foundation models, which can be used for a diverse number of tasks if only we can adapt the model, say by fine-tuning it, say by adding on extra components on top of it. And we almost think that this could be seen as just like, let's say, paleontology, or say the geological history of the world. There's this Cambrian explosion, the idea that all these species came about, a long time ago and exploded into this variety that we see on Earth today. So it seems that these foundation models might give birth to that kind of explosion in AI. But one of the problems that we face is that this is also associated with what I'm calling a supernova in model size. In fact, the growth in model sizes has accelerated exponentially, and this is actually quite a recent development, where some of the largest models in the world today, the ones that are publicly known, are perhaps in a couple of hundreds of billions of parameters. So if you think about what a billion parameters means, that's a billion parameters is say around 4 gigabytes of storage. And when you get up to hundreds of billions of parameters, you're starting to talk about terabytes just to store all the different weights in the models. And all this growing model complexity and data size is, on the one hand, it's perhaps how these foundation models live up to their promise of being able to diversify to so many different applications. But on the other hand, simply manipulating, handling one of these models, let alone even training or putting them into production requires not just a lot of hardware, but a surprising amount of expertise in order to get all that hardware running. And so that led me to the question that how does anyone expect to be able to create AI applications on these foundation models if you can't even operate the model, whether that's by having the hardware, but the people to use it? And to give you a bit more of a concrete sense about just how much it costs to operate one of these models, one of my favorite examples here is really to compare what's the cost of, say, the transformer models and architecture and try to put that in some real world terms. How much energy does this model take to train? What could you use it for in terms of, say, powering cities, powering homes, driving cars from city to city? So if we took a modest model, let's say about 2.3 billion parameters, this is, say, about 2 orders of magnitude below the state of the art today, but it's certainly considered big for most people that have only access to a limited number of GPUs. Well, according to some recent publications, apparently just training one of these models to completion takes about 206,000 kilowatt hours, and that's the same amount of electricity that it would take to send in 2,000 electric cars 300 miles to another state. So it's a surprising amount of energy. And that gets even worse when you consider how in the typical model development process, you might be retraining these models hundreds of times perhaps. You might need to iterate on the architecture of the model. You might need to do hyperparameter optimization. You may need to retrain and fine tune it with new data. So if we just took 100 times retraining of this model as a kind of straw man figure, then we're talking about energy usage at the level of 20 gigawatt hours. And not only would this take 20,000 years to train on a single GPU, it's also the amount of energy that's required to power 2,000 typical homes in the United States of America for 365 days. And, where are we going with this? Well, if we're going from 2.3 billion parameters to some of the largest models to date, 175 billion is OpenAI's GPT-3. Several models that are under review right now have apparently exceeded 600 billion parameters. Just a simple extrapolation will show you that this is sending the energy cost into the realm of terawatt hours. And to put it in context, right, 1.5 terawatt hours, that's the entire city's electricity usage for 365 days. And even if you try to train this on a single GPU, not only would it take over 1 million years, you can't even fit the parameters onto its memory, because 175 billion parameters is approximately in the range of 600 to 700 gigabytes of memory. So all of what this is saying is that you can't avoid having to use distributed computing for some of these large and promising foundation models. But at the same time, some of the costs here, in terms of especially the energy and environmental impact, has gotten to a point where you could almost say it's a little bit irresponsible. And so there's also, I think, this growing realization that we need to reduce the cost to be a bit more realistic, a bit more responsible. And it's not just that we need these, distributed ML systems for very large transformer models. You sometimes have to ask the question, what about new hardware architectures, such as, say, running these models in a non-data center, or heterogeneous computing environment, such as, say, on the edge or on mobile? What about if, say, transformer is no longer the most popular architectures 5 years from now? Just as, convolutional neural networks and recurrent neural networks gave way to the transformer architecture, what's going to happen in the next few years? Will any of these systems still be relevant and usable by then? And what about some of the more, say, interesting data settings, non-IID data, private data, say in federated learning, and even some of the tasks that go beyond training? You still have to put the models into production, and that means running them on inference. And you also want to do some experimentation loops, such as active learning, reinforcement learning. So not only do you need ML systems for a wide variety of practical, practical applications inside machine learning, but at the same time, I talked about how there's a lack of expertise, and it's really hard for most ML researchers, or most graduate students, most researchers, even many engineers. The different concepts in ML systems are frankly quite challenging for non-systems experts, because there's many different aspects to consider, from how you encode the messages to how you communicate them over the network, and even the fine optimization details, such as how you manage scheduling of different memory reads and writes, how you partition that storage across different devices. All of these things add up to a large body of requirements and expertise that's not easily met these days. So kind of to summarize what I've been talking about, The challenges in ML systems, I kind of divide them into three major themes. One is the high hardware and environmental cost of machine learning, especially with the growth in model sizes. Then number two, there are many different unaddressed ML settings that are, I think, just as important as the training setting, but not much attention is being paid to them. And three, ML systems are a hard topic for non-systems experts, and we have to figure a way to bridge that gap between what a systems expert is capable of versus what a person who's maybe able to download code off GitHub and maybe run it on a typical computer. What kind of experience would we like them to have? Would we want them to be able to manipulate these large models and perhaps perform, all the all-important research on them? I think these are some of the challenges that I'd like to address in my talk. So just as if I've outlined three different problems that I'm thinking about, I also want to talk about three types of, three different directions in which I see possible solutions. The first one, communication, is really about how we can reduce the hardware or environment cost of ML by allowing distributed systems to be a lot more efficient than they are today. And the second topic, composable ML systems, is about putting together different ML building blocks, ML systems building blocks, in order to address various new and different ML settings, and also to be able to assemble these systems in a way that is a bit more automated and more accessible to non-experts. And lastly, as kind of a tangential topic to the first two, I'd like to talk about the art of deciding what to measure, the metrics that we used in ML systems research, and how some of the existing metrics are, I think, skewing the focus of the community, and how having the right metrics could result, I think, in a new perspective and a new direction on how to perform SysML research in a way that's a bit more, equitable, fair, and accessible to everyone. So without further ado, let's begin on the first topic, which is communication. So just as a little bit of preamble, the setting I'm addressing here is, I think, one that everyone in this audience will be familiar with. It's your typical iterative convergent ML algorithm, such as stochastic gradient descent being one of them, but this also applies to Markov chain Monte Carlo algorithms and to some extent even federated learning algorithms. You have an objective function with data X and parameters A, and you're performing this iterative convergent update where the parameters A are being updated by an aggregation function F and an update function delta. So for example, in stochastic gradient descent, delta is really the function that computes the gradients on each data sample, and F is simply the function that sums all of those gradients together and applies them to the parameters A to get the next iteration's parameters. Okay. Now, let's talk about some numbers to give you an idea of why distributed ML is both difficult and costly in terms of hardware, costly in terms of computing time. And that's because communication across distributed systems is actually very bandwidth limited when compared to the speed at which a GPU can process the gradients, calculate the gradients, and assemble them for stochastic gradient descent. So if we think about how large a transformer network can get, let's just use that as an example. Something that's over 100 billion parameters would require 400 gigabytes of storage if stored in 32-bit floating point. Now, the best case communication bandwidth you're going to get between GPUs on the same machines today is about 600 gigabytes per second, and that's with the latest generation of NVIDIA GPUs. Of course, if you have access to, I think, some of the state-of-the-art hardware that some startups are manufacturing, such as perhaps you might have heard of the wafer scale engine by a company called Cerebras Systems, then some of this bandwidth does get a little higher. But by and large, if you're buying NVIDIA hardware, this is about the best you'll get. And that's just within the same machine. Now, if you talk about what's the bandwidth between different machines on a network, in the best case, you're going to get about 25 gigabytes per second with InfiniBand. And in the worst case, it's going to be Ethernet, and you'll have something less than a single gigabyte. Now, what that means is that even with very good hardware, you can maybe transfer the entirety of the parameters of the large transformer network one time per second. And if you're not using good hardware, then you're going to transfer it one time every 20 seconds or even one time every hour. So this is a difficulty with very large ML models that a lot of people have trouble getting around, even if they have access to distributed machine learning software. And so one of the themes of my research in the past has been on understanding how to get around these communication bottlenecks. And to say a little bit about how these communication bottlenecks come about, I want to talk a little bit about the way in which most ML systems or even most parallel ML algorithms function. Almost all algorithms today use a type of synchronization that historically computer scientists have called bulk synchronous parallel. It's an idea that's shown up in MapReduce, Google's MapReduce. It's shown up in Spark, the big data system, and about practically every distributed ML system to date. And the way this kind of strict consistency of bulk synchronous parallel works is that devices will compute updates, which I denote by this function delta, in between these periods that we call global synchronization barriers, which roughly correspond to the boundaries between, say, stochastic gradient descent iterations, for example. It's during these barriers that the aggregation function, where you sum up all of the different gradients to get the the overall gradient direction, that's when that's computed. And people use this because it very naturally corresponds to how most parallel algorithms work. In the systems literature, we call this serializable execution, meaning that it has the same outcome, the same guarantees as a sequential algorithm. But kind of the weakness of BSP, especially in the distributed case, is that anytime there's a load imbalance, and a load imbalance can happen for many reasons. One is by the nature of the data. Two, it's by the nature of how the model's parallel work is being divided over machines. Or three, in a data center setting, you may be sharing your computational resources with other scientists. You may be having other users on the network, and these can cause machines to slow down or perform less quickly than you'd expect. So the problem with BSP is that if machines can slow down for any reason, be it load balancing or having other users on top of it, then you get what is known as a straggler effect, where some machines will be faster, some will be slower, but the time required before each barrier is always going to be determined by the slowest machine. And so you're basically taking the worst case time for every single machine. And while this might be small, if you have, say, a small cluster with maybe 8 machines, once you get to the scales that are required to train a large transformer model, for example, it's been estimated that these 100 billion parameter transformer models require at least hundreds, if not thousands, of distinct machines to train. Then even the slowest machine, the slowest out of 1,000 machines, is probably, in all likelihood, going to be quite a bit slower than, say, the average case or even the fastest machine. And that's where bulk synchronous parallel suffers from throughput problems that can make scaling. When you think about scaling, you want, if you had put, say, 100 machines on a problem, you'd expect it to be 100 times faster. But when using bulk synchronous parallel, it's not uncommon to end up only, say, 25 times faster instead of 100 times, or even 20 or 15 times faster. And so you have to ask, where did all that performance go? What happened? So one of the solutions that I've worked on in the past is a type of substitute for bulk synchronous parallel that I call stale synchronous parallel. It's what we call a bounded asynchronous consistency model, where you give every device a little bit of flexibility. We know that there's always going to be faster and slower devices because of stragglers, because of load balancing effects. So let's allow devices that are running slower to not hold back those devices that are running faster. In other words, devices that are running faster should just proceed to the next iteration using the currently available copy of parameters. Don't worry about the updates that are missing from the devices that are slow. But we don't want this to get out of control, so we put a bound. There's a staleness limit, say s equals 3 in this example, where if the fast device gets too far ahead of the others, say 3 iterations further, then it's going to have to stop and wait and give others a chance to catch up. And the nice thing about this type of bounded asynchronous consistency is that in most cases, straggler effects are random. So this allows, eventually device A will catch up naturally, as it might be device B's turn to become slow due to, say, user load, network load, or load balancing effects. And what this does is that it gives everyone a chance to catch up without some other device running too far ahead. In the era before deep learning, my collaborators and I showed that still synchronous parallel accelerates quite a large variety of ML applications, to the point of being about roughly 5 times faster than even well-optimized bulk synchronous parallel baselines. Now, that was in the era before deep learning. Nowadays, what has happened is that SSP has had, I think, quite an interesting impact on how ML systems are constructed in the deep learning era. So for example, here I'm going to talk about a couple of papers that were not from myself or from my collaborators, but from other people that took the SSP research that we did and then created new systems on top of it based on this still synchronous parallel idea. So one of these systems is a system that performs parallel training of deep learning models using something that we call pipeline parallelism, where you can think of that as different layers of a deep learning model are assigned to different machines, and data flows into the first machine, the first layer, which then computes its activations, goes on to the second machine, the second layer, all the way to the top, then comes back down to do back propagation, calculating all the different gradients. With these kinds of pipeline systems, one issue is that to get high utilization, you want to have every machine working all the time. That's what's shown in this figure. So that everyone's computing on some data sample at some point, causing the entire pipeline to be filled. But when you do that, because pipelines have this staircase-like construction, where some machines will be finishing their computation later than others, what you get is a situation where some machines will need to proceed ahead of others with older versions of the parameters. And this is exactly what the still synchronous parallel system in theory allows. Also, the cool part about this paper that I found really cool is that they actually used different GPUs in the cluster. They were not using the same homogeneous hardware. It wasn't, say, all A100 devices or all DGX2s. It was different GPUs from different editions, different generations. And all of this heterogeneity is something that's a strength of SSP. SSP is able to manage very heterogeneous GPU clusters and dealing with the types of asymmetric layers that you would often find in, say, non-transformer models, such as convolutional neural networks, or even some transformer models may have asymmetric sizes. And that all of that creates load imbalances in pipelines that are easily rectified by applying SSP theory to it. And then there have also been other applications, such as decentralized deep learning for, say, federated applications. I'm not going to talk too much about this, but again, the key concept here is that the flexibility of SSP enables these types of heterogeneous applications to thrive. And last but not least, SSP has also been used to perform fault recovery in a cheaper and faster fashion. Traditionally, you would do fault recovery by reverting to the last checkpointed iteration. But what SSP theory shows is that you do not have to restore the entire checkpoint. It suffices to simply restore the devices that crashed or failed, because you can kind of characterize that under SSP theory as a bounded loss of serializability. That is to say, it's totally okay to have part of the machines recover and all the other machines continue to use their latest parameter versions. Okay, now I've talked a little bit about how SSP enables all this heterogeneity and this kind of partial recovery. And I want to give a bit of intuition as to why this is possible theoretically. So SSP, and in fact, there's actually an entire family of SSP models, including something that we call eager SSP. The key idea is that they closely approximate the sequential or serial execution of a parallel ML algorithm, causing what we call a bounded loss of serializability. That's to say, the error in the parameters that results from allowing machines to go faster or slower is always bounded by a certain window, which is given by these green boxes over here. The key formula here is that up to a certain number of updates can be either out of place, which means that they might be early, they might be late, but it's never more than this amount. So as the number of iterations goes to infinity, this error window is always a fixed size, and that's what leads to convergence. And that's been covered by my collaborators and myself in a number of theorems, which I would just briefly flash here, so you know that these the idea of SSP is actually theoretically well justified. And what's most important is that we've developed both regret and expectation bounds that hold even when the noise in the parameter trajectory due to SSP is non-IID, which of course will happen in cases where there's a lack of, say, proper load balancing, or there are other, say, users on the cluster. So that means the speed of the different machines is not, say, a homogeneous distribution, but it varies depending on the local environment of each machine. And that's actually the key why SSP is able to be used in heterogeneous systems. It's an advantage that other solutions to distributed ML do not have, because they often rely on an IID assumption in the noise. There have also been other theorems that go beyond the regret and expectation bounds to further bound the distributions of staleness inside SSP. You can basically think of that as saying that, okay, I want to know, it's all well and good that some machines are faster and slower, but can I have some guarantees that most of the machines will actually be close to zero staleness? How do I know that most of the machines are behaving well and maybe it's only a few that are out of place? Well, without going into too much of the details, we've developed the theoretical bounds in both the distribution as well as the variance of the staleness. And these bounds we've been using them to show that in practice, SSP implementations usually perform just as well as bulk synchronous parallel in terms of the accuracy of the parameter trajectory. That's to say, the staleness is close to zero. And it's only a few machines that really go out of bounds. Okay, so that was the end of the first part of my talk, which is on how we reduce communication costs in order to enable distributed ML systems to scale much better than they would have otherwise. Now I'm about to talk about composable ML systems. This is the second theme of my talk. And to motivate this section, I think if we look at the history of how ML systems are developed, because they're always developed for whatever is the most popular model architecture at the time, we saw a wave about 10 years ago of ML systems for pre-deep learning models. The two most popular ones during that time were systems for topic models and systems for boosting. And then just recently, maybe this is about 8 years ago, we started seeing systems for convolutional neural networks, recurrent neural networks, and perceptron fully connected layers and networks. And today, the systems are all being developed for transformer networks. And if you take a look at some of the key diagrams from some of the papers that have been published recently, such as NVIDIA's Megatron LM system and Microsoft's DeepSpeed system, you'll see that they have a lot of very specific optimizations for the transformer architecture, which is all well and good. That's how they're going to get the systems to scale. But the problem of this is that what happens in about, say, 3 or 4 years, when someone comes up with the next great architecture, and then all of these systems can no longer be applied because they're all transformer specific. So, and that's a big problem for all of us, because if I'm used to, say, downloading these systems off, say, a GitHub repo, and I find that a few years later they don't work, who am I going to turn to? Do I have to wait for another systems researcher to publish the next system before I can run some of these models at scale? And so that motivates the idea of composability in ML systems. It's not about achieving perfect performance on a given model or given architecture, but it's about achieving broad and good enough support for various model architectures, both old, current, but also new ones that we have not seen yet, but we anticipate will surely be developed as the art and science of AI continues to advance. And in order to talk about composable systems, I need to talk about something that we call strategies. Strategies are basically a combination of ML systems design software architecture as we put together different components into a system, and maybe specific optimizations for different parts of the models. And formally, we say that the strategy is made up of instances of aspects of systems and distributed ML. We want to have systems that can ultimately automatically compose strategies for a given model. And I'm going to talk about how we can achieve that in this part of the talk. Because this is a fairly complicated topic, I also want to talk a bit about the outline. I'm going to start first by giving a few examples of what I call monolithic strategies. These are the types of strategies you see in famous papers, such as the parameter server paper, such as papers promoting the use of all reduced in MPI or some other collective communications library. And these strategies, I also want to talk about why composed strategies are superior to monolithic ones. And then finally, I'm going to talk about some of the algorithms and systems that help us to automatically compose a strategy. So let's start with a classic example of a monolithic strategy, such as the parameter server. If you're not familiar with distributed systems ML, a parameter server is basically a master-slave architecture where the slaves are the different, say, machines with GPUs on them that compute gradients, and the parameter server is a central machine that aggregates all the gradients in order to update the parameters and then distributes them back to all the different machines. Classical, kind of systems architectures that has been used for more than a decade in systems and machine learning. And another one that's been popular, especially recently, is a strategy called ring all reduce. And in this strategy, instead, it's not a centralized strategy. You can think of it as a decentralized strategy, where every different machine will compute part of the gradient, and then they will exchange in a ring fashion. So that's in like, just like you're placing, let's say children are playing musical chairs. They're all going to take, circle around the different chairs. And so we pass the messages around in ring fashion. And then by passing the messages around and aggregating them locally at each machine, eventually the entire system comes up with the full parameter update on every machine. Now, here's an interesting thought. What if we take parameter server and apply it to one part of a model, and take the all reduced strategy and apply it to a different part of the model? Would this result in better performance than, say, running the parameter server for the whole model, or all reduced for the whole model? And it turns out that the answer is, in fact, yes, because ML models, especially deep learning models, because they are heterogeneous with different types of layers, convolution and pooling layers at the bottom, and say fully connected perceptron light layers at the top, it would be very natural to assume that they benefit from different topologies just because they are different beasts in the first place. And more specifically, in the typical, say, convolutional neural network, there are much fewer parameters, unique parameters in the convolution and pooling layers. But in the fully collected layers, based on the layer sizes, it's easy to see, say, millions, if not hundreds of millions of different parameters over there. So with this difference, one can apply the parameter server strategy to the pooling and convolutional layers, which have a small number of frequently updated parameters, and then a different strategy that we call sufficient factor broadcast, which is a way of decomposing matrix updates into vector style updates, thus reducing the communication cost from quadratic down to linear. And this complex strategy, where we've applied a different strategy to different layers, greatly outperforms the strategy where we only use one of the other on the model. And this is not just limited to convolutional neural networks. There's a second example where inside language model pipelines, it's possible to apply the parameter server onto the recurrent layers inside the language model. Now, this is in the era before transformer models, so this is a slightly older example. And then in the embedding layers, we apply, it's the other way around. In the embedding layers, we apply the parameter server strategy. And on the recurrent layers in the language model, we apply the all reduced strategy. So essentially, as long as there is heterogeneity in ML models, there's always an opportunity to, if we had the right automatic system, to easily apply different strategies onto different parts of models. Now, then the next question is, well, how does one actually come up with these strategies? Do you have to design these strategies by hand? In fact, the two examples earlier on the convolutional example and the language model example, those were examples of hand-designed strategies, and then they were hand-implemented, hand-optimized, and papers were published on them, which is all good and nice. But if I'm not a systems researcher and I want to apply it to my model, then and I don't have the expertise to hand-design these strategies, then am I out of luck? Well, as it turns out, one can formulate the problem of coming up with a strategy as an optimization problem that essentially takes, you want to maximize some measure of goodness of the representation of the strategy. So you take a strategy, you take a model, and you take computing resources R, and you can compile that into a systems representation, and then search over the space of systems representations to maximize the goodness variable T in this example. And in solving the strategy optimization problem, there's a little bit of a flow chart here. You want to have a way, you can't analytically search over the space of all strategies. That would be intractable because you're essentially looking at a graph problem and trying to apply different strategies to different parts of the graph. But you could, of course, use approximations by, say, using a biased sampler, and by biased, I mean in a good way. It uses domain knowledge to pick strategies that were known to work for similar layer types. Let's say for convolution layers, I knew that parameter servers work well, or for embedding layers, say parameter server works well as well. And then by sampling these strategies in a biased way and converting them to systems representation, you can enter this closed loop where you estimate the goodness and then rank all the different strategies, select the best one, and then actually do a little bit of trial run on it so that you get an accurate measure of the goodness. Because now you need to go from a theoretical estimate into an actual empirically measured estimate of the performance. And then you feed that back in order to prove the estimation algorithm. Now, there's this big black box here, which is how do you actually estimate the goodness of a strategy without running it? And again, we want to do this because running the strategy is expensive, right? I have to get all the GPUs lined up. I have to use computing hours to do that. And I need to test a lot of different strategies before finding the right one. But it's not going to, be cost effective if the amount of time taken to find the strategy is longer than, much longer than training the model. So we need to have a way to estimate the goodness. And one of the first ways we tried for this was to actually construct an expert model where we would say for each layer, there's different types of features we can talk about, right? Going down to what's the variables, the size of the variables. Is there a certain compression method that's been used? What kinds of structures, placement, bandwidth, replicas? Model all of that into a function. And then, this gives us a function that is pretty easy to compute, and we can get the goodness of a particular strategy that goes to the simulator. But the problem with this approach is that it doesn't generalize well. For one, you have to frequently update this expert model to keep up with different advances in not just ML systems, but also ML modeling. Like if I have captured all the variables for convolutional neural networks, but I didn't do it for transformers, then when transformers came out, I would have to also update all of my variables and create a new model by hand. So it's kind of very labor intensive to develop these. At worst, it's not just labor intensive, but requires a systems expert to develop these. So it feels like we're back to square one here. If I've got something that I want to have a system that auto-generates strategies for architectures I've never seen before, but if I have to keep updating the expert model, then doesn't that defeat the purpose? Well, as it turns out, there's actually a better solution for this, and that is to actually simulate the goodness function by using a learning approach, a machine learning approach itself. So we take the system's representation of the strategy and its actual execution trace. So we do this, we collect a data set of different strategies running on different models and their execution traces, and we just train an embedding model for this. the embedding models architecture can be anything, but specifically we've used recurrent neural networks and graph attention models on it. And then we use this embedding in a downstream model to predict, okay, what's the execution trace going to look like for previously unseen architecture? What are the different metrics and measures of goodness that will come out of a strategy, such as its compute costs, such as the amount of, say, time taken, such as, say, the amount of communication bandwidth used. And what's interesting about this approach is that by essentially running machine learning on execution traces and strategies, you can then find strategies for previously unseen architectures that are actually up to about 60% better versus both, very highly specialized and efficient, but single strategy systems, such as parameter server systems and all reduced systems that cannot, say, put different strategies on different parts of models. But it also outperforms even some of the literature's hand-tuned strategies, where people have a favorite model and they spend a lot of hours optimizing it just to get every last, drop of performance out of it. And this happened a lot, especially during the era where ImageNet competitions were popular, and basically everyone was trying to optimize for VGG and ResNet. So with this systems representation simulation, we can do better than, say, existing systems by coming up with these composed strategies automatically. And we also have some evidence to show that even when we train the simulator on small models, because we might not have the resources to collect the trace on a very large model. If we did have the resources to do it, then we may as well just train that model, right? So if we just collect traces on smaller models, we find that the simulator itself generalizes well to larger models. And the way we quantify this is that if we do the embedding on small models and strategies versus doing no embedding, we end up with about 50% better performance. Okay. So kind of the last piece in this story is that we need to actually run the strategies after we've come out with. Everything up before this was how to automatically create a composite strategy. And then to actually run it, we've also developed an open source system called Autodist. It's a part of the formatting here. It's an open source tool that essentially takes the model, computing resources, and strategy, which may be auto-generated from, say, a system like the one I just showed, or perhaps handwritten for someone that has expert knowledge and wants to try out a specific strategy. And it converts that into what we call a runnable systems representation that can be inputted into an execution system such as TensorFlow. So essentially, it's natively compatible with TensorFlow. The output of this takes a strategy and model and all that, and outputs something that can directly run in TensorFlow's data flow graph execution system. And with that, it actually kind of completes the loop, and you're able to run these auto-generated strategies in practice, on your favorite system without any kind of, say, strong systems ML expertise or background. So I'm now into the last part of my talk, but I realize I've been, speaking for half the talk now, and I wanted to check with Lee if there were any questions I should be answering at this point.
No, at the moment, please go ahead. We can ask the question near the end. All right.
Okay, thanks, Lee. So this last part of my talk is about, it's about kind of a topic that most people don't really ask or talk about, but turns out to be pretty important. And that's basically, how do we measure what's going on inside an ML system? How do we know that we're measuring the right quantity in order to compare our system with other systems? And this is an interesting topic because in machine learning, most of us are used to measuring task performance for a specific domain of expertise. We might be talking about accuracy or F1 scores. If we're in NLP, we might be talking about BLUE scores and, say, benchmarks like specific benchmarks like SuperBLUE. If you're on computer vision, you might be talking about metrics like IOU. So everyone's got different metrics for their different ML domain. And then in systems, there's also two kind of more generic metrics. One is throughput, which is basically how many data samples do you process per unit time. And the other is statistical efficiency, which briefly you can think of as how much progress on the objective function curve that you make per data sample. Now, all of these metrics actually have different limitations when it comes to comparing ML systems, and I'd like to talk a little bit about those limitations. So first of all, task performance, while it's definitely very important for individual domain researchers in their specific NLP or computer vision or say general ML domains, it really isn't a good metric for ML systems for a number of reasons. For one, we're all aware that task performance is a very compound measure that's influenced by many factors. Data quality, whether training data set or validation data set, the shape of your loss function, initial values, algorithm hyperparameters, even certain domain best practices that are sometimes not communicated in papers, but are just assumed to be there. And ultimately, if you take a look at any real convergence curve, especially say validation accuracy, it can go up, it can also go down with the x-axis for reasons that are sometimes very hard to debug or even to understand. So ultimately, it's a noisy and misleading measure of ML systems performance, and you really don't want to be using this to compare different systems. So what about throughput? Throughput is a very simple measure. How many data samples you process per unit time. But increasing throughput often can conceal drops in the other metric, which is statistical efficiency. For example, if you were to use asynchronous distributed computing over the bulk synchronous parallel that I talked about earlier, you'll mitigate stragglers and thus increase throughput, but you also introduce staleness into computations, so the statistical efficiency actually drops at the same time. Another thing that people sometimes do is employ large batch sizes in mini-batch training. So what this does is that it increases the scalability. The larger your batch size, the more GPUs you can use in parallel at the same time and still maintain a certain level of utilization efficiency. But increasing the batch size also changes the characteristics of your convergence. And in general, you're going to see decreased progress per data sample. And statistical efficiency is kind of like the opposite of that. You want to maximize statistical efficiency. If you want to do that, you desire highly synchronous execution, small batch sizes and learning rate, even fine-grained scheduling of model updates. But all of that comes at the cost of throughput. And it's something that a lot of researchers that create parallel algorithms, but don't really have a lot of experience in writing ML systems, what they don't realize is that when they take their highly statistically efficient algorithm and actually implement it in practice, it doesn't scale well. You end up with a curve that basically plateaus and doesn't increase with more computing power. Okay, so in my research with my collaborators, we've worked on a metric called goodput, which you can think of as a composite of throughput and statistical efficiency. It's designed to capture both the information and throughput and the information stat efficiency. And I like to think of it as how we measure the useful throughput. It's a number that basically goes between 0 and 1. So it's also bounded above and below, which makes it kind of nice. And so goodput captures both the system's choices that go into affect throughput, but it also captures the choices that jointly affect throughput and statistical efficiency. And I'm not going to read out these things, but there's a lot of different factors in systems design and architecture that could make one of these go up while making the other go down at the same time. And what you actually see in general is that for any kind of dimension in which you can slide left and right and affect statistical efficiency and throughput, it's almost always the case that sliding in one direction will increase, say, throughput, but decrease statistical efficiency. You slide in the opposite direction, you get the opposite. And it turns out that then, because goodput is throughput times efficiency, you end up getting a kind of parabolic curve in most cases. And the goal really of most ML systems is to find those configurations of different, say, system architectures, different systems choices that will maximize goodput by finding that sweet spot where throughput times efficiency is maximized. So as it turns out, the idea of measuring goodput can actually be put into practice and generate a system that can automatically tune itself, or at least automatically tune a set of configuration hyperparameters so as to maximize the goodput of the currently being trained ML model. And in order to do that, we need to actually develop a model of the two terms, throughput and efficiency. On this slide, without going into too much detail, the message here is that throughput can actually be pretty easily modeled by just measuring a lot of different systems quantities, such as batch size, synchronization time, number of GPUs, and just putting them into an equation allows you to get a pretty good model of throughput that, when put to the test, actually captures pretty well how ML models perform on different numbers of GPUs, or different numbers of machines. The more interesting, in my view, quantity is how to model statistical efficiency. And here we've actually had to develop some new mathematics and theory in order to account for this. Efficiency is really a measure of how much noise there is in the gradients. So let's say we're using stochastic gradient descent. It's a measure of how much noise there is versus how much signal there is inside these gradients. And quite briefly, one can measure this using a quantity called the preconditioned gradient noise scale, which accommodates not only algorithms such as SGD, but also can handle what we call preconditioned algorithms, of which the well-known Adam optimizer is an example. And kind of the intuition here is that when the gradient noise is high, you can use larger batch sizes and thus improve throughput without hurting statistical efficiency. I think the intuition here is basically that when you have high noise, using a large batch size actually helps to make the gradient, so because the gradient after all is an average of all the different gradients, data sample gradients within the mini batch. So when you average over a large number of gradients, you want to see that as much noise as possible is removed. And that's only possible if there's a lot of noise in the gradient to begin with. And this actually turns out to be empirically a pretty good model of statistical efficiency. It's not completely perfect for every single model, but it works well enough in order to, when combined with the throughput modeling, allows us to pretty much predict good put for a given ML model running on a different number of GPUs and machines at a certain batch size and learning rate. And so this leads us to basically applications of good put, where now that we can model good put, we can actually run an optimizer over good put in order to solve for what are the best hyper-configuration hyperparameters for the system that would thus maximize good put. You know, as I kind of showed a few slides ago, good put functions tend to be these parabolic shaped functions. So it's pretty easy to search for the peak using a basic search techniques. And ultimately, what we're trying to do is we're trying to find the right batch size for a given ML model, as well as the right learning rate that accompanies that batch size, so that we can maximize the good put, which is ultimately to say, I want this model to train as fast as possible. So I'm going to find the best batch size and the best learning rate given the number of GPUs I'm running on. And that's the key, because with different numbers of GPUs, that optimal batch size and optimal learning rate turns out to be different. Right. With this kind of good put optimizer, it enables an application called elastic resource scheduling. So you can think of this as a kind of a cluster admin's dream scenario. You have a fixed number of GPUs on a cluster over different machines. You have many different jobs running on it. And you want the cluster to say, let's allocate resources in such a way that all the jobs complete as fast as possible. I can shrink the job, say put in a few more GPUs if I think it's going to be more cost effective on this particular job. Conversely, I can take away GPUs from another job if I feel that it's not making good use of those extra GPUs. And using this kind of good put optimization idea for elastic resource scheduling, you can actually get up to 50 to 70% faster, even versus say pretty well implemented scheduler systems. And by well implemented, I mean that you won't find these in your typical, say, Slurm scheduler that's distributed with most, cluster setups. These are schedulers that are very specific to deep learning and have to be kind of installed and configured in order to realize these performance gains. And what we're seeing with good put optimized scheduling is that it's even 70% faster than some of these optimal baselines. Another interesting application from good put optimization is this idea that on the cloud, you might have, say, differently priced computing resources. And if any of you have ever used Amazon Web Services EC2, you'll know them as spot instances. These are, GPU instances whose cost changes depending on time of day, depending on how much money Amazon is making at that point or how few people are using it. And you can actually apply this good put optimization idea to scale up jobs when resources are cheap, and then scale back the number of GPUs when resources get more expensive, all to fit within a certain cost, how many dollars you have, what's your budget. If I have, say, $100 to spend this job, then good put optimized scaling is going to find what's the fastest way I can complete this job within $100, and given the fact that the spot instance price is changing all the time. Okay. And maybe just as a side note, the other nice benefit about good put optimization is that it actually results in more fairness in how the cluster jobs are run. So if you're a systems administrator or you run a lab cluster, you always have to contend with the issue where, okay, different people are fighting for resources. And some people are saying, hey, I need to use half the cluster for the next 3 days in order to run my experiment. And then other people are saying, well, I only have small experiments, but I need to run them for a very long time, say the next 2 or 3 weeks. So sometimes it's very hard to decide what's the fairest way to allocate resources. And good put optimization gives a new perspective on it. It basically, because good put optimization systems can understand how much a job benefits from adding more resources or how much it's penalized for taking away GPU resources, it's able to organize these jobs in a more fair way. And by fairness, we mean that essentially life is not perfectly fair, but we try to get fairness within a number that we call rho, the finish time fairness, and we try to keep it between basically 0.5 to 1.5, which kind of suggests that most jobs are treated more or less fairly. Okay. And last but not least, all of this is actually available. This good put based optimization system is available in an open source package we call AdaptDL, which is a piece of software that plugs into PyTorch and then auto optimizes many jobs in the background. Okay. So that's the end of my third theme, and I'm going to just take a few more minutes to share some of my closing thoughts and directions that I'm thinking about these days. I think the first thing on my mind is that there's a lot of opportunities for advancements in ML systems to not just improve what I call the high end, and a lot of effort today is going into making those transformer models run bigger, run faster, and run in an even larger scale with even more data. But I think there's a lot of other costs that we might want to think about, such as even after you've trained it, training the model may actually turn out to be a small cost compared to the inference cost, especially if you think about how Google does 3.5 billion searches a day, or the environmental costs of running these water-hungry data centers, which apparently use billions of gallons of water per year. That's something that I was pretty surprised when I heard about that. And in addition to sustainability, I think the discussion I just gave on metrics and good put is actually just to tip the iceberg, because good put is ultimately still a measure that's of performance. It's kind of like a measure of performance in a closed world where we don't care about the impact on the environment, we don't care about the impact on society. But what about measuring? Is there a way to more systematically measure the environment and cost impact of different models? Are there perhaps greener ways models that maybe aren't as big or fancy or high performing in terms of task metrics, but which have a much lower environmental impact, cooling water use, dollars in time, memory size, the list goes on. And the third theme I do think about sometimes is, as the topic of federated learning picks up steam, right? People have started to think about a world in which ML is a bit more decentralized and democratized than it is now. When I started as a PhD student, right, I always thought that machine learning was a pretty, democratic field, in the sense that anyone could pick up MATLAB and run a machine learning model of it and get results out of it. And then, as the years pass by, we now live in the world where the biggest models are run by only the most well-resourced organizations. And, I sometimes ask, what does it take to bring some of these powerful but massive and costly models out of the big organizations, to these smaller to medium-sized research organizations, small businesses, etc., or even go further as a kind of a decentralized public good? Now, this is something I don't have the answers to, but I think as the Stanford Foundation Models paper, as it thinks about some of the societal consequences of foundation models. I think this is a question that's worth addressing. Okay. Right. As a final closing remark, I want to say that some of the work I've talked about in this talk today is part of a broader open source ecosystem called CASL, which stands for Composable ML Models and Pipelines, Automatic Tuning, Scalable ML Execution Systems, all supporting machine learning needs. And today's talk was about included two systems rather, AdaptDL and Autodist. But the larger ecosystem includes projects on composable NLP, such as Stave, Texa, and Forte, and on automatic hyperparameter tuning and model tuning, such as Tune. And this ecosystem has been integrated with, I think, many partner organizations, Hugging Face Models, Berkeley's Ray project, Microsoft EdNI, and PyTorch, just to name a few. We even had blogs featured on the different ecosystem pages of our partners in a way so that we are co-promoting each other's projects and building a more robust and open ecosystem. Okay. And this is just kind of an illustration of how different CASL components come together in some of the work that my startup, Petuum, is doing, right? We've taken the different CASL components and put them into a technology stack in order to run various natural language processing models, visualize the output, but also, train them and schedule them over a cluster using Autodist, AdaptDL, and Tune. Okay. And in closing, I'd like to thank, some of my current collaborators, people I've worked with closely over the past couple of years. There's Auric Chiao, graduated from CMU, is now actually Petuum's Chief Executive Officer. Willie Neiswanger, who's a postdoc at Stanford and also, a member of Petuum. Hao, also a member of Petuum and a postdoc at UC Berkeley. And Eric, who, as we all know, is president of MBZUAI. He was also my thesis advisor, and he's also the founder of Petuum Inc. And this is just a small list of people that I've worked with. It's the people I've worked with on systems ML in the past couple of years, but there's a whole long list of other collaborators I've been in touch with over the years, and I also want to thank them as well. So with that, that's the end of my talk. Thank you all for being good listeners, and I'm happy to take questions now.
Thank you very much, Qirong. It's a very nice talk. And then I'd like to start with some questions. You mentioned about this decentralized training, democratized training. How much aspects of privacy preserving computing is integrated into your system?
Mm-hmm. Yeah, this is a very good question. And I think the question about privacy preserving, my perspective on it is that it's extremely important, but also the federated learning community has not come to an agreement on what's the best way in terms of algorithms to preserve privacy. So by that, I mean that if you take a survey over the federated learning landscape, you'll see some people advocate model parameter exchange. For example, the classical Fed average algorithm, the first so-called federated learning paper, never exchanges gradients. It avoids the privacy issue altogether by just exchanging model parameters over the network. And then, in the other direction, you have people going for differential privacy in the gradients itself. So they essentially, tweak or distort the gradient in a way to such that privacy is preserved. I do not actually have the ability to foretell or prophesize which of these two directions will win out. Will the model sharing philosophy be the one that wins out, or the gradient sharing philosophy be the one that wins out? But my perspective as a systems ML researcher is that I want to be able to ultimately support either of them. And that's actually why composable ML is important. We need to be able to have the components that can be swapped out at will, depending on how someone chooses to formulate and solve their privacy problem with data with gradients. So I realize that's a bit of a cop-out because I haven't answered the question, but I genuinely believe that it's a question that it's best answered by the federated learning community as a whole. And then my job as an ML systems researcher is to support what ultimately proves to be effective.
Great. So the second question is, nowadays, graph data become prevalent in many places, such as e-commerce and finance. yeah, this graph can be billions of nodes and hundreds of billions of edges, and on top of it, there will be something like a graph neural net also become very popular.
Yes.
That this type of data is a bit different from this type of vector data. Yeah, you mostly focus on. What is your thoughts on building system for that kind of data? Right.
Yeah, no, I think that's super exciting. Just for everyone's information, Lee and I used to work on graph data a long time ago. And I think that because graph data is fundamentally non-IID data, right? The types of algorithms and models you run on them basically operate on very different assumptions. So that actually goes a little bit back to some thoughts I had on the still synchronous parallel model, right? I mentioned that its strength really is that the theory for still synchronous parallel does not rely on IID-ness inside. Here IID-ness doesn't refer to the data, but refers to the heterogeneity in the system that causes the different delays, the different noise, right? So I think that's also that. I suspect that there's a theoretical connection between the fact that this type of still synchronous parallel delay theory and system and the way that graph data is done IID. I suspect that there are ways to essentially graph data is very heterogeneous, and it's probably possible to construct a system that takes advantage of the fact that ultimately, if you look at a classic algorithm like, say, belief propagation or page rank, right? We all know for sure that different parts of the graph influence each other in more or less ways depending on the connectivity. And I think there's a lot of space in terms of how we approach heterogeneous problems, whether that's heterogeneous data like in graphs or the heterogeneous systems required to do them. Today, graph neural networks actually were quite a topic in systems conferences this year, where I think even at OSDI, there were at least 4 different papers on graph neural network systems. But all of them were relying on the classical idea that, okay, I can take one of a graph execution system, such as the data flow system, which has been done for more decades in systems research, and put them on these, and I'll get very good results. And that's absolutely true. Everyone expects that to happen. But what if there were a different way to approach the problem that would allow the graph to be learned on more flexible hardware? After all, the graph is sometimes decentralized, right? Especially if you talk about a decentralized application. So if I'm going to have decentralized hardware, how am I going to run a graph neural network on it in an efficient way? I think basically looking into the science of communication, especially delayed communication, may reveal some insights. I haven't done a lot of thinking about that, but my belief is that with that growing interest in graph neural networks, I suspect especially the federated learning or the place where you basically cannot share data freely, that kind of scenario is where some of the research I've done in the past might prove to be interesting.
Great, thank you. There's another question. Here you've been talking mostly about making the learning algorithm easily usable and efficient in existing hardware. Would this, for instance, give maybe some clue on designing better system as well? Or have you think about algorithm system co-design to make it more efficient?
Right. So I guess by design you mean hardware design.
Yeah, is that maybe new type of hardware, right? Beyond just using a big GPU cluster.
In fact, the truth is, especially in recent years, the pace of custom hardware development is actually accelerated. I think what has happened in particular is that with the model size explosion, especially caused by transformers for the last couple of years, it's becoming increasingly difficult to get high utilization across a cluster of conventional GPUs. And that's in part because there's so many parameters that you can only fit a tiny fraction of the model on a GPU. So once you start to slice and dice the model up this way, it's very hard from an optimization perspective to get high utilization when everybody is holding a very small piece of the problem. So, of course, the solutions I've been working on are trying to kind of lift that constraint by making the individual small, weak, low-powered device. I mean, GPUs are not low-powered, but they're low-powered in the grand scheme of transformer-sized models, right? And so you want to make the different GPUs perform better with higher utilization, despite the fact that they only see a tiny part of the problem. But of course, people are designing larger and larger chips. Like I think everyone in this room must have heard about, how Tesla is creating a architecture called Dojo, where they tile basically a lot of small chips together. And I believe what's going to happen is that they will design a data flow compiler to route different computations to that grid of chips. So it's actually pretty exciting, even from the software perspective, what I suspect they're trying to do. But this will, of course, it will, of course, change what is optimal. Co-design, it's always been a truism that in any generation, hardware designers are always responsive to changing trends in software. But I believe that ultimately, and it gets to this slide about composability, right? Mm-hmm. I cannot forecast what aspect or what technique is going to be popular in 3 or 4 years. I'd be pretty much a fool to do so. But what I think is viable is to construct the systems that allow the aspects to be reassembled in different ways, such as this example of taking 2 strategies and putting them into one system. If I have the capability to reassemble strategies for a single model, then if the underlying hardware changes and the strategies are no longer valid, I can always have that system search for new strategies and apply them, right? It's actually kind of the maturation of the ML and systems community to take a more compiler-like approach. Like in software compilers, say if we're old enough to still be programming in C++, we don't think about how the C++ code is translated down to hardware, because the compilers are now so sophisticated. And every hardware manufacturer, with its, say, whether you compile to an Intel processor or an ARM processor, they have their own optimized compiler to make sure that code runs as fast as possible, right? So this idea of composable ML systems is really about compiling ML programs down to the hardware, where that hardware may be a big GPU cluster full of DGX machines, or maybe it's a more modest AWS cluster, or maybe it's one of the new chip designs, right? It's about creating that foundation and framework for that compilation to happen. So that's my perspective on it.
Okay, great, thank you. And any other question from the audience?
Yes, please.
Please go ahead.
I have one question.
You go ahead.
Okay, so is our architecture, I mean the CASL architecture, based on specific hardware, I mean the GPU, can we expand to IPU or other AI chips?
You are, I guess you're talking about MBZUAI's cluster setting, and your question you're asking, I guess, is does it make sense to invest in new hardware beyond, say, NVIDIA GPUs? Is that how I should understand your question?
Because in the front of the presentation, you analyze the bandwidth from the GPU inside the different GPU inside the one machine, and the GPU from different machine. The IPU designed, the motivation is increase the bandwidth from different IPU. So your metric, the good put, is to and your design is based on this this architecture to increase the bandwidth. So the IPU increase the bandwidth too. So if we expand our hardware, expand our architecture to IPU, can we get some performance, better performance?
So just as a little bit of a gentle correction, the good put metric isn't actually related to the bandwidth. Good put is agnostic to hardware. It applies whether you're doing it on NVIDIA hardware or other types of chips or CPUs or whatever. It's equally applicable to both. In this specific case, however, what do you mean by IPU exactly? What does the I stand for?
The IPU is from GraphCore.
GraphCore's IPU chips. I see. So this is just my personal opinion.
Pardon? We have a port 4. There will be 1 MK 2K and port 16 with 4 MK 2K and the port 64 with 16 there, and they are connected by the optic cable, 100 gigabyte cable. So that's the IPU, a short description.
I see. So I'm not familiar with the network connectivity for GraphCore IPUs. I do know that roughly speaking, every GraphCore IPU is about similar in computational power to your typical NVIDIA GPU. So based on what you've just told me, it sounds like what GraphCore is focusing on is to increase the amount of bandwidth between their IPUs. I would say that it doesn't hurt for MBZUAI to have 1 or 2 GraphCore machines in order to perform systems ML research and benchmarking. But I will caution that the problem is that you can only put so many IPUs with high-speed interconnect, right? So the thing about networking is that high-speed interconnections are very expensive in terms of dollar cost to actually make the interconnects. So you're always going to run into a point where GraphCore can only squeeze so many IPUs into one high-speed mesh or fabric. And then if that number of IPUs doesn't have enough aggregate memory to say take a 100 billion transformer model, then you're still forced to send that model across different, say, network meshes. And then you run into this limitation where even the most powerful InfiniBand setups are down to only a couple of, say, tens of gigabytes per second. So the answer is not straightforward. It really depends on what is the largest model that you can run on the GraphCore hardware in terms of its memory capacity. That would still be such that all of the IPUs are connected via the high-speed interconnect we talked about. So I cannot answer that question because I don't actually know the network layout or hardware of the GraphCore setup you just described. But I will state generally that it's always beneficial for MBZUAI, in order to be a leader in systems ML research. It's always good to have 1 or 2 alternative architectures on hand because that's where some of the new research opportunities in systems design can show up. So I hope I've at least tried to answer your question partially.
Okay, thanks. Another question about the auto dist.
Mm-hmm.
It's a restrict to TensorFlow, right?
Yes, you are correct. Autodist is restricted to TensorFlow, and the reason for this is that it's an unfortunate technical reason that PyTorch does not have a good API for forming and manipulating its graph representation.
You mean the Keras, right?
Not Keras, PyTorch. It actually doesn't matter whether Keras is used or not because Keras is not an execution system. Keras is I'll call it a library that runs on top of TensorFlow or PyTorch to specify and construct models. But ultimately, what matters is as TensorFlow and PyTorch compile the model code down into an intermediate representation. TensorFlow compiles it into a data flow graph. PyTorch has a imperative execution mode where the graph is not explicit. And unfortunately, Autodist needs access to the graph in order to reorganize it and construct the strategy. The way it actually constructs strategies is by manipulating the graph to create the different computational patterns that reproduce a parameter server or reproduce, say, or reduce. So the collaborators that worked with me on Autodist, they are currently focusing most of their attention on TensorFlow for this reason.
The TensorFlow, what the version, the latest one, or 1.x or 2.x or something?
I believe Autodesk works with 2.x TensorFlow, but I also want to state that that we're working on a new version of Autodesk that allows us to incorporate even more different types of auto-generated strategies. This system, which is called Parrots, being done by my kind of collaborator Hao Zhang. It's probably still about, I'd say, some time away before release, but I just want you to be aware that there's a successor version to Autodesk coming up.
Okay, about the Adapt DL, is it restricted to PyTorch?
So currently it's because this is an open source project, it technically isn't restricted to PyTorch. It could be made to work on TensorFlow, but we chose to make it work on PyTorch in part because Autodesk works for TensorFlow. So we wanted to have a system that works for PyTorch, knowing that a lot of ML researchers actually choose to use PyTorch over TensorFlow. So for the moment, it works only on PyTorch. But if we had a larger, say, a set of willing open source contributors, I could imagine that it's possible to make it work on TensorFlow as well.
One more question. About the CASL architecture, I noticed the old Adapt DL provides some Docker file. About the Autodist, there are Kubernetes and Docker too. So if something is managed by Docker, then it can be managed by the Kubernetes too. So the CASL architecture is managed by Kubernetes, right?
I think the better way to say it is that Kubernetes is one of the choices to manage CASL. So each of the CASL components is actually able to run standalone. So the way they combine together in this architecture is that basically within Petuum, we've created systems that at the bottom, we are running Kubernetes and running AdaptDL, Autodist, and Tune kind of at the layer above. And then using AdaptDL to run TensorFlow and PyTorch models created in Forte and Texar. So really the way you can think of it is that there's no strict dependency. You do not have to use Texar with, say, AdaptDL. You're not forced to use Tune with, say, Forte or Stave. It's all very flexible. And in fact, we actually intentionally designed all of this software to be downloadable and runnable on a single machine, because we know that's how people try and adopt open source. So there's a very strategic reason behind this. But that said, for some of the projects, especially the scalable projects where the benefit is realized by running it on several machines, it then becomes important if you're running several machines to have a management system for those machines. And in industry practice, it's very common to use Kubernetes and Docker files. And that's actually why we provide them. So the context with Kubernetes and CASL is that it's not a requirement. It's there because the users of AdaptDL and Autodist are most likely to use Kubernetes. But everything can be downloaded and run on a single machine. It does not require Kubernetes or Docker files to run.
So I have a GPU cluster server, hardware, I mean, and should I have another server to install CASL to manage that GPU cluster, I mean the hardware?
I see. So the Texas, Stave, and Forte tools can be downloaded and run on any existing cluster setup. Because they work at the same layer as Keras, basically. So they very much plug into TensorFlow and PyTorch without too much fuss. Now, if one wants to use Tune, then the recommended way to do it is with Microsoft's NNI interface. And that does kind of require you to set up the NNI software on a cluster, and then Tune is a plugin into NNI. And then for AdaptVL on Autodist, I believe AdaptVL specifically does come with the correct Docker files to be deployed on a Kubernetes cluster. So my recommendation, if you wish to try AdaptVL in particular, is you need to have Kubernetes set up. Autodist is a bit more. It doesn't require Kubernetes, but does require that you install Autodist on every machine. And ultimately, each project has its own set of instructions on how to run it individually, as well as how to run it in an integrated fashion with other components. But there's basically no, say, how do I put it? There's no single super system like Kubernetes that you can currently download to run all of that on top. It's a problem that we're still thinking about, but we recognize that each of these projects is led by different leaders, and so they have their different technical priorities, but we try to make sure they interface and work well with each other.
One last question. Is it recorded? I need to go through it more times.
Yeah, it's recorded.
I mean.
Yeah, okay, great. Yeah, it's recorded. Right, thank you for the question. Any other question for the other people? And probably we can take one or two questions. Any other question? Okay, great. If no more question, and let's thank Qirong again. Thank you very much for the talk. It's a really nice talk. Yeah, thank you. Yeah,
thank you. Bye.
Right.
Let me see. There's thank you. Okay, see you then. Bye.
Bye.
So Ali, will I be seeing you in 30 minutes in the other Zoom?
Yeah.
Okay, well, see you then at I think 7 p.m. your time then.
Yeah, see you then. Bye.